We are now recording. Let's get the slideshow set up from this slide. Let me go over just a couple of minor issues that are going to affect my office hours the rest of this week. First, I will be out of the office. Usually I have office hours 10:45 to 12:30, okay, on Tuesdays and Thursdays. Today, I will probably be out of the office for about 15 to 20 minutes in that time frame. I've got to run somewhere for my physical science class before it starts at 12:30. So today I will be out of the office just a short time, 15, 20 minutes in those office hours. Probably be right close to 12:30, 12:15, something like that, okay? Number two, on Thursday I'm taking that class on a field trip. So that means either tomorrow, well definitely tomorrow afternoon. Normally my office hours are 3:15 to 5:15. However, tomorrow I've got to go to the Birmingham campus to take the paperwork to get the vehicle to drive the class to the field trip. So I will be out of the office some tomorrow, 3:15 to 5:15, probably shortly after 3:15. I'll probably work the rest of the time on the Birmingham campus, okay? Next, Thursday, we're going on the field trip, and if I can't pick up, in fact, I'm probably going to have to pick up the vehicle sometime between 10:45 and 12:30, okay? So I'll probably leave shortly after this class is over with and book it on over to the Birmingham campus to get the vehicle and then head back here. So I will be in the office part of the time, but not the full time. And then Friday, normally I'm on the Birmingham campus 7:45 to 1, but I have my annual physical at 8 o'clock Friday morning, which means I'll be at the clinic at 7:45, not here, Birmingham campus. So I hope the physical won't take more than an hour. Hopefully it's the first one in the morning, so you won't be behind yet. And hopefully I won't have to do blood work because I'll be doing some later in the month and you can piggyback those together. And that there'll be no other delays, and I hope to be back on campus, Birmingham campus, by 9:45 or 10, somewhere in that time frame. So all the rest of this week, I've got some sort of little problems with office hours, but after that, they should be much more regular, I hope. All right, any questions before we get started today? Okay, where we left off last time was wondering why Amber wasn't here, but now we quit wondering. Okay. Okay. All right, this is where we left off, top of page 316, chapter 4, trigonometry, 4.6, graph of the other trigonometric functions, and here they are. This is the review, the summary of this section. Your basic tangent function, y is equal to tangent x. No A, no B, no C, no D, okay? Just y is equal to tangent x. Or let me say that again. A is equal to 1, B is equal to 1, C is equal to 0, D is equal to 0. This is the basic tangent function, okay? Domain, all real numbers except the places where it's not defined, which is where cosine is 0, that's at the half pies. So all the half pies is not defined, so therefore you have vertical asymptotes at every half pi. The range, all real numbers, negative infinity, positive infinity. Tangent and cotangent are the only two trig functions that normally have a period of pi. Now that's with note, with A is equal to 1, B is equal to 1, C is equal to 0, and D is equal to 0, the period is pi. In fact, it doesn't matter about the others. As long as that B is 1, the period is pi. Okay? Now the tangent, once you've done all that, the key points are your minus half a period, okay? That would be minus pi halves, minus pi quarters, 0, pi quarters, and pi halves. Now the half pies, you already know, they're vertical asymptotes. Draw those in first, okay? And then halfway between those vertical asymptotes, you've got your y-intercept. I mean x-intercept. It is, in this case, y-intercept too. And that's at 0. Halfway in between the intercepts and the asymptotes and the intercept, you have the point where the tangent function is at -1, and between the intercept and the second asymptote, is at +1. So -5/4 -1 +5/4 +1. Now, if you have an A that's a vertical stretch, this value here, rather than be minus or +1, will be minus or +A, whatever that A is. Okay, that's at the quarter pi, plus or minus. If your B is something other than 1, that changes your period. Pi over B is your new period. Okay? If you have a C, that's a phase shift, that can shift it right or left depending on the sign of the phase shift. And if you had a D and they haven't given any like this, that would be a vertical shift, and you just move up your equilibrium point up or down, depending on the sign. Now, with that done, let's go to cosine. Cotangent x. Y is equal to cotangent x. Again, A is 1, B is 1, C is 0, D is 0. Okay? Cotangent is 1 over tangent, or I like to think of it as cosine over sine. Either way you think of it, everywhere that either sine or tangent is 0, that's at the whole pi, that's your vertical asymptote here. Okay? So you remain as all real numbers except your whole pi's. Okay? That means your half pi's are going to be your zeros. That means your quarter pi's are either going to be +1 or -1. If you had an A there, they'll be +A or -A. If you had a B here, your period will be pi over B. Okay? Your range again, just like the tangent, all real numbers. Okay? First thing I do, again, the key points. One asymptote, another asymptote. That's one period. Okay? Like 0 to pi, whatever. The 0 and pi and 2 pi and negative pi, those are your vertical asymptotes. Halfway in the vertical, between the vertical asymptotes is a 0. And whereas tangent function, as long as there's no sign out front, SIG as a sign, strictly increasing function, cotangent strictly decreasing. Okay? Now, if you had a sign out front that changed that, then flip it over, same thing here. Any questions? Sine or, tangent or cotangent? Okay? Secant or cosecant? Actually, you might think these are the most complicated to draw. They are the easiest, in one sense. In another sense, for a cosecant, because that's 1 over sine, first thing you do is draw in your sine curve. Okay? And let me get my pen activated, and I will do that. What color you want me to use on the sine curve? Red? Okay, it's already red. Okay, so the sine starts at 0, goes to +1, 0, -1, 0, +1, going backwards, -1, 0, +1. So here is your sine curve, something like this. First thing you do, draw the reciprocal function. If it's cosecant, draw in the sine. If it's secant, draw in the cosine. Let's go on and draw the cosine in over here. Starts at 1, goes to 0, goes to -1, goes to 0, goes back to 1. Going the other way, a 0 and a -1. So the cosine function, cosine function looks like this. Okay? Draw that in first. Okay? So I'll draw the reciprocal of either secant or cosecant, whichever you're doing. Draw that one in first. Everywhere you get a 0, vertical asymptote, vertical asymptote, vertical asymptote, vertical asymptote. By the way, same places that you would have for cotangent. Okay? On the secant, cosines are 0 at the half pi's, negative half pi, positive half pi, 3 half pi, 5 half pi, negative half, 3 half pi, all those, everywhere that cosine is 0, draw in a vertical asymptote. Same vertical asymptote you use for tangent function. Okay? Then, everywhere you have a peak for your sine, they kiss at the peaks and the valleys. Okay? The cosecant touches there and goes up, whereas the sine touches there and goes down. Where you have a valley on sine, you have a peak on cosecant. They kiss there, and cosecants go down while sine goes up. Over and over and over. They touch at the peaks and valleys, and then they go in opposite directions from there. The secant and cosecant are always approaching the vertical asymptotes, depending on what direction they're heading. Pretty easy to draw. The key points you cover when you do the sine or the cosine function, and you're used to doing this, okay? And the rest of it is just vertical asymptotes, peaks, valleys, and going in opposite directions. So, cosecant, domain, all real numbers x except your whole pi, because that's where sine is 0. Your vertical asymptotes are at the whole pi. So draw those in first. The range, everywhere from negative infinity to negative 1, and then picking up at 1 and going to positive infinity, including the plus or minus 1. Period is 2 pi because the sine period is 2 pi. Same thing for secant, except the domain is all the real values x, except where cosine is 0, and those are at the half pi's. Okay? And the range is the same, period is the same. Vertical asymptotes are just shifted over to the half pi's. They kiss at the peaks and valleys and go in opposite directions. Done. Any questions? All right, that's the last slide. Oh, let's see, I don't want to do that maybe yet. Let me just hold off of that. Let's do vocabulary. Top of page 317. The tangent, cotangent, and cosecant functions are blank, so the graphs of these functions have symmetry with respect to the tangent, cotangent, and cosecant. They're all what? I wish I hadn't done that. Okay, let's go back to this. They didn't mention that here, but they did otherwise. Let's do some current slide. Okay. My word, how far back did we go here? Ooh. Here we go. All right. What can you tell me about tangent, cotangent, and cosecant? What do those three have in common? Cosecant, tangent, and cotangent. Has to do with the even and oddness. Tangent, cotangent, cosecant. What are they? Any guesses? Earth students, come in, please. Okay. Any guesses? They're all odd functions, okay? So these are odd, so the graphs of these functions have symmetry with respect to the origin. Excellent. Okay, number 2. The graphs of tangent, cotangent, secant, and cosecant all have what kind of asymptotes? Vertical asymptotes. Excellent. To sketch the graph of a secant or cosecant function, first make a sketch of its blank function. Say again? It's what? They're all trigonometric. Yeah, but they're all trigonometric functions. What do we call what do you graph first when you're doing secant or cosecant? Okay, not exactly inverse. It's really close. Reciprocal. Later we'll talk about inverse functions, and that's a different concept, okay? It's the reciprocal functions. which are sines and cosines. Okay. Number 4. For the function f of x equals g of x times sine of x, g of x is called the blank factor of the function f of x. The blank factor. Woo. Let's look right here. What's the title of this section? Subsection. Damped. Be sure you put the P in there. Okay. All right. The damped factor of the function f of x. I like to say dampening. They like to use damped. Okay. Number 5. The period of y is equal to tangent x is blank. Period of y is equal to tangent x. Before I moved the slide, it was on the slide, but I changed it. What's the period of tangent? Normal period of tangent. Boy, I just went over it. Period for tangent. Pi, exactly. Okay. Number 6. The domain of y is equal to cotangent x is all real numbers such that what? Domain of y is equal to cotangent x is all real numbers such that x is what? It's what? We're doing cotangent. X cannot equal x. You're right that it can't be, huh? All your powers of, multiples of pi. 1 pi, 2 pi, 3 pi, 0 pi. Yeah, so 0 was right, but it's not the only. You finished? Okay, so you could come back sometime. Okay.
Thank you.
Yeah. I did mistake something. Well, no. She doesn't care if I mistake it. Okay. So the domain of y is equal to cotangent x is a set of all real numbers such that x is not equal to pi halves plus n pi. Just can't use the half pi's. Number 7, the range of y is equal to secant x is? Okay, negative infinity to negative 1 and 1 to positive infinity. Perfect. Okay, number 8, the period of y is equal to cosecant x is? Period of y is equal to cosecant x is what? 2 pi. Excellent. Homework exercises, you've been assigned most of these. I would do all of 9 through 14, but check your answers for the odds 9 through 13. It's helpful to do them all and check the answers for 9 through 13. Then do any of the odds 15 to 37, any of the odds 39 to 47, any of the odds 49 to 55, any of the odds 57 to 59, to 63, either 65 or 67 or both. Any of the odds, either 69 or 71 or both, either 73 or 75 or both, any of the odds 77 to 81, and either 83 or 85, whichever you choose, or both if you want to do those. The exploration, not a bad idea to look at 87. It's a true-false. Don't see many of those on the test, but take a look at that. 89's a good one to think through. 91's a good one to think through. And 93, at least think about it, because that's the title of it. Think about it. All right, any questions? Okay. All right. Get out of 4.6 and go to 4.7. Next to the last section in the chapter. Of course, you'll be having a test when we finish 4.8, which isn't going to be all that much longer, okay? So let's get the slideshow from the current slide. Continuing trigonometry, now we're doing inverse trigonometric functions. Earlier today, we said inverse when we really should have been saying reciprocal, because there's a difference here with functions. Inverse function is different from the reciprocal function. So what we're going to do is evaluate and graph the inverse sine function, evaluate and graph the other inverse trigonometric functions, and we'll evaluate the compositions of trigonometric functions, which sort of doesn't fit that much with inverses, but it does a little bit. So let's start with inverse sine function. Reminding ourselves from Math 112, which you all took here, right? We did inverse functions, period. What was special about an inverse function as opposed to a function? There's one requirement for a function to have an inverse beyond what the requirements were for it to be just a function. Anyone remember what it was? Second? The range. Okay, there is something special there. Whatever the domain of the function was becomes the range of the inverse function. Whatever the range of the function was becomes the domain of the inverse function. If that's what you meant, absolutely true. Anything else about inverse functions or functions that have inverses? Something else had to be true that was not true for regular functions. What was the test we used for regular functions? How can you tell if a graph represents a function or not? How can you tell just by looking at any old ordinary graph whether that's a graph of a function or not? There's a simple test we look at. The vertical line test. Great. Okay? Does the vertical line test itself ensure that you have an inverse? Just the vertical line test. Yay or nay? No. Okay. All right. There is another test we have to do to see if a function has an inverse. What would that be? It's not the vertical line test. It would be the horizontal line test. Very good. If it passes the horizontal line test, then you have a one-to-one function. Okay? Now, in general, does y equal sine x? Okay. So we know that for a function to have an inverse function, it must be one-to-one. That's what I was trying to get you to say earlier. That is, it must pass the horizontal line test. Now, you know from the graph of the sine function that what? It does not pass the horizontal line test. Right? Because it repeats itself over and over and over again. Any horizontal line is going to intersect it an infinite number of times. Okay? So what must we do? Restrict the domain to a one-to-one section. Okay? And here is the graph of y is equal to sine x. Okay? Now you could take any portion of that graph that is either strictly increasing or strictly decreasing. And that could be a one-to-one portion. So this portion from this peak to that valley, that's one-to-one. Here to here is one-to-one. Here to here is one-to-one. Okay? Lots of little pieces you can do. We generally take minus pi halves to pi halves. That portion there is strictly increasing. This is the graph of the sine function. So that's usually what we use for the one-to-one portion. It's not one-to-one everywhere. Fails the vertical line test. If you go past either a maximum or a minimum, it's going to be going in the opposite direction. It failed vertical line test. So as long as you stay between a max and a min, or a min and a max, you're on a one-to-one section. So what we do, we restrict ourselves to minus pi halves to pi halves as the domain of the part of the sine function that does have an inverse. Now, what would be the range of that sine function in those values? What does the range measure? The y values, and what are the accepted values for y value, but when x is going from minus pi halves to pi halves? Yes, -1 to +1. So that's your range. So this portion is 1 to 1. It passes the horizontal line test. So it does have an inverse. What would be the domain of that inverse then? Who else to that? Okay. What would be the, what we're just saying is, for a sine function to have an inverse, it has to be 1 to 1. 1 to 1 means it has to pass a horizontal line test. Since the sine function repeats itself periodically, it can't pass a vertical line test until you restrict the domain, and if you do, you have to restrict it to strictly increasing or strictly decreasing portion. Technically, generally we go from minus pi halves to pi halves, strictly increasing. Okay? So that portion is 1 to 1. It does pass the horizontal line test. So therefore, that portion of the sine function does have an inverse. What would be the domain of that inverse sine function? Domain of the inverse sine function. Domain of the inverse sine function. -1 to 1 is exactly what the range of the sine function is. Okay? So what would be the range of the inverse sine function? Negative pi halves to pi halves. You flip them. Okay? Very good. So sine x has an inverse function only on this interval, or definitely on this interval, minus pi halves to pi halves. You can't go anything past negative pi halves or past positive pi halves. If you do, it starts curving back on you. Wouldn't be 1 to 1. All right. However, when you restrict the domain to the interval minus pi halves to pi halves, corresponding to the blackened portion of that graph that we just looked at, the following properties hold. On that interval, negative pi halves to pi halves, the function y is equal to sine x is strictly increasing, and on that interval, negative pi halves to pi halves, y is equal to sine x, takes on its full range of values, -1 to +1. On that interval, negative pi halves to pi halves, y equal sine x is 1 to 1. It passes the horizontal line test, and it has an inverse. Okay? All those are true. So, on that restricted domain, negative pi halves to positive pi halves, y is equal to sine x has a unique inverse function. That means it has one and only one inverse function, and that's called the inverse sine function. And it's denoted two different ways. The old way, or at least in my mind it's the old way, was the arc sine. Okay? Now, I think that comes from the association of the central angle with its intercepted arc length on the unit circle. Okay? That's the best guess of why it's called an arc sine. To make it like every other function we deal with back in pre-calculus 112, pre-calculus algebra, we take the function and put a -1 there. Okay? That means inverse sine. That does not mean reciprocal of sine. If you had 3 to the minus 1, that's 1/3. If you add x to the minus 1, that's 1 over x. If you have a function to the minus 1, that means inverse, not reciprocal. Okay. So the notation inverse sine function is consistent with the notation inverse function, the inverse function of f. Okay. The arc sine notation, read as the arc sine of x, comes from the association of a central angle with its intercepted arc length on the unit circle. And if you remember, what goes here is an angle, okay? And this is a measure of the y value for that angle x, okay? Now, when you do the inverse sine, like here or here, this is the angle, that is the measure. Okay, so remember that. Something that refers to an angle for in a trig function is the argument of that trig function. And that gives you a number. Those numbers have ranges on them. Okay? When you're doing the inverse sine, the thing that follows the inverse sine is the number, and the thing on the outside represents the angle. So that's why it's talking about the relationship, association with the central angle of the intercepted arc. Okay. And Jasmine's here. Good deal. Slowly getting here. So arc sine x means that the angle or arc whose sine is x. So that gives you the other way of thinking of this. Another way of expressing this concept here is x is equal to inverse sine of inverse sine. They switch them back here. The inverse sine of y is equal to x, or sine of x is equal to y. If you have this in place, that's what was given. Y is equal to inverse sine of x. That means the sine of y is equal to x. You take the opposite function, the inverse function, move it to the other side and delete it from the first. Okay. Both notations, arc sine and inverse sine, are commonly used in mathematics. So remember that inverse sine of x denotes the inverse of the sine function rather than the reciprocal of the sine function. What do we call the reciprocal of the sine function? It has a name. Reciprocal of the sine function. We just were talking about it before you came in. The what? Say again? I can't hear it. It has its own little trig name. No. Arc is the same as inverse. What is reciprocal? It's also called the reciprocal function of sine. There are 6 trig functions, right? Sine, cosine, tangent, cotangent, cosecant. You're absolutely right. This is a cosecant. It's not an inverse sine. Okay. How rapidly we forget. Okay. Now, here are some of the key points here in graphing, say, the inverse sine. As we just said earlier, what was the domain of the sine, minus pi halves to pi halves, becomes the range of the inverse sine of the arc sine. Remember, for an arc sine or inverse sine, this is the value, those are angles, minus pi halves to pi halves. Okay? So, the domain of arc sine are the values that was the range of sine, minus 1 to 1. So here's what you do, set up a minus 1 to 1. That's going to be the domain of inverse sine, or arc sine. And they're going to go from, the range has got to be from minus pi halves to pi halves. Okay? and then you just have to assign them accordingly, okay? And guess what? 0, 0 is going to be on both sides, sine or inverse sine, because you flip the x and the y value. So that's got to be the same. And because sine is an increasing function between minus pi halves and pi halves, that means that the inverse sine also has to be an increasing function between minus 1 and 1. So you've got your points, minus 1 minus 1 pi halves, 0, 0, plus 1 plus pi halves. And you can put these other points in there if you want to. I find it easier just to do that. Here's the other thing I like to remember. The sine function has a horizontal tangent line here and there. Here it's very close to 1. That looks like, you just look at that and you think that is the identity function. Y is equal to x. Okay? So when you're doing the inverse sine, now rather than a horizontal tangent, you have a vertical tangent. Each of those, but you still have a 1-to-1. That looks like y is equal to x. So this portion looks almost identical. Because remember, your inverse functions reflect across the identity function. Okay? And that's exactly what that's doing. Where this looks like an identity function on either one, it's going to look like it on the other. But then when this is horizontal on the other, it's going to be vertical here, horizontal on the other, vertical here. So that's the other thing I remember to help me get the curve going in the right direction. All right, any questions about that? Okay. So bottom of the page 320, definition of the inverse sine function. Inverse sine function is defined by y is equal to arc sine or y is equal to inverse sine, both notations being the same. If and only if sine of y is equal to x. In other words, you take the sine of both sides, sine of y becomes sine of y. You take the sine of the arc sine, inverse functions undo each other, so that leaves you only the x. Now, where x here or here goes between minus 1 and 1 inclusive, you know that here, it's also true here, and the y's go from minus pi halves to pi halves. Here is the range, here is the domain. Okay? And the domain y is equal to arc sine or y is equal to inverse sine is minus 1 to 1. Minus pi halves to pi halves. Does that make sense? Just reverse of what you would have for the sine function. Does it make sense? Okay. Let's do example 1. If possible, find the exact value of arc sine of -1/2. Now, how do I go about doing that? Whoops. Let me tell you my approach. I think the book kind of does it the same way, but here's what I do. Let's give that a value, a variable. Name a variable. I don't care what. A? Is that what you said? Okay. Let this equal A. All right? Now I want to rewrite that equation in terms of a regular trig function, not an inverse trig function. So how do I do that? How do I do it? Say again? I can't hear you. Yeah. Not an arc sine or an inverse sine, but as a sine. Rewrite that as an equivalent equation using regular trig function. Sine. We just did it. It was just in the definition. Want to go back and see the definition? Here it is. Y is equal to inverse sine of x if and only if Sine y is equal to x. You take the opposite function on both things. So, let's do this one. What would be an equivalent equation? Say again. Yeah, but he said A. I like Y better, but he likes A. Okay. Sine of A is equal to. Say again. What did it do here? It's whatever followed arcsine. What follows arcsine here? Negative 1/2. Okay, I feel like a dentist. Okay, pulling teeth here. Okay. What's that?
You don't do the inverse of negative 1/2?
No, we're not. Okay. If you mean reciprocal, no, don't ever think reciprocal when you're dealing with inverses. Only if it's a multiplicative inverse. With functions, we're not thinking inverses. Reciprocal at all. Okay? What you do is take the sine of this side. The sine of the arcsine is just the number that's left. Because the sine undoes arcsine undoes sine. So that leaves you just a number, and when you take the sine of this side, you get sine of A. Now the question is, what angle A, when you take the sine of it, you get negative 1/2? Angle A, when you take the sine of it, you get a negative 1/2. Okay. What are some angles that when you take sine of it, you get negative 1/2? You need. Say again? Okay. Let's draw a unit circle. If nothing else, let's go back to the unit circle. Okay? Now, remember where we're limiting ourselves to when we're dealing with sines and arcsines. Pi 6? Okay, pi 6 would be right about there. This would be 1/2 there. Negative pi 6, that's better. Down here, that would be negative 1/2. Exactly. A is equal to negative pi 6. Okay? Couldn't that have been over here too, though? You'd have a negative 1/2 there too. Could it have been? Remember when we're doing this angle over here would also have a sine of negative 1/2. Why don't we use that one? Okay. Well, this is negative down here too. Why don't we use that one over there? Where are we dealing with? Whoop, right here. You're having to stay between minus pi halves and pi halves. And you see over here, that's between here and there. This is where you're limited to. You can't go over here. That's outside the domain. Okay? So that is the correct answer. A would equal negative pi 6. Okay? How about that next one? Sine to the minus 1 of root 3 over 2. What does that mean? Or how would you approach it? Set this equal to some variable. Which one do you want to use? Say again? B? Okay. We're sticking with the early part of the or because this is question B part of the question. Okay, y'all are clever. Okay? Can you rewrite that equation in an equivalent format? An equivalent equation but doesn't deal with an inverse. Sine of what? B is equal to square root of 3 over 2. Can anyone think of what angle B that could be? Pi thirds. Excellent. B is equal to pi thirds. Fantastic. That would be up here. Okay? Root 3 over 2. Perfect. How about this one? What might you set that equal to? C. I thought that might be. Okay? Can you rewrite that equation into an equivalent equation? Sine C is equal to 2. What angle sine will give you, angle C will give you a sine of 2? Value of 2. Angle C, when you take the sine of it, do you get a value of 2? Any ideas? Anybody? There aren't any. No! Sine stays between plus and minus 1. You can't ever have a sine of an angle being 2. So this does not possible. Even for Tom Cruise. Never. Impossible. Okay, no. All right. Y'all okay with those? I'm going to erase my scratch. Okay. Let's see what they do. Because, and they start with telling you the answer and saying, therefore it's the answer. It's sort of a dumb way to do it. You know, I would say set that equal to a variable like we did. A, B, or C, X, Y, Z, whatever you want to name it. And then you say sine of A or sine of X or sine of whatever is equal to negative 1/2. That's what that says. And then say, well, the angle has to be this. So if they say, because this angle works, that's the answer, okay? Which is a little bit, to me, of a backwards way of doing it. But if you had chosen another angle that did, but it wasn't in between minus pi halves and pi halves, you can't use that. You have to use an angle in between minus pi halves and pi halves. So therefore, the arcsine of this is minus pi 6. Okay? Angle whose side is negative 1/2. Whose sine is negative 1/2. B part, and again, they say, because this answer works, that's the answer. That's sort of a dumb way of doing it in my mind. I would say because sine of B is equal to root 3 over 2, what has the B got to be? And it's got to be between minus pi halves and pi halves. Well, it's positive to put it in the first quadrant. What angle in the first quadrant has a value? The sine is root 3 over 3. That's pi thirds. So therefore, that's your answer. Good deal. And then C, it is not possible to evaluate y is equal to inverse sine of x when x is equal to 2 because there's no angle anywhere who has a sine that's equal to 2. Sine is always between minus 1 and 1. 2 is outside that. There is no angle that will give you an answer of 2. Not possible. Remember, the domain of the inverse sine function is minus 1 to 1. 2 is outside that. No answer. Not possible. Okay, moving on to example 2. And by the way, there's a checkpoint there with only 2 possible ones. I would do those checkpoints because you can always, if you can't figure out what the answer is, the audio video solution is at larsonprecalculus.com. Okay, let's go to example 2. Sketch the graph of y is equal to arcsine of x. Okay. Where I would begin, where would you begin? You tell me. Okay, what are you going to do there? Say again? Okay, let me give you a hint. Let's label our axes. Wouldn't that be a good thing to do for graphing something? Figure out what your axes. Now, what do we call the values we might want to put on the horizontal axis? That would consist of your, what goes on the horizontal axis? Values in your horizontal axis represents which variable? Dependent or independent? Horizontal axis represents which variable? Dependent or independent? Say again?
Dependent.
Do you say dependent?
Sure.
No, the horizontal axis is always independent, okay? Because that's the one you get to choose. If you're a cheerleader, you say, give me a X, okay? You choose the X, then that determines the Y, okay? Give me an X, that will determine the Y when you take arc sine of it. So that's called and what do you call the set of all the independent variables? The values for the independent variables. It has a special name. Okay. Say again? Domain! Excellent! Domain, speak up, okay? So what is your domain of the horizontal axis? For inverse sine or arc sine of x, what values can x take on? -1 to 1. Perfect. Goes from -1 to 1. That's all it can be, because remember, something that follows the sine is going to be an angle, and the other thing is going to be a value. When you're doing inverses, the value follows the inverse of the arc sine, and the only values that a sine can take on are plus or minus 1, somewhere there. So I don't need the outside parts, okay? Now, what might I do with the vertical axis? Goes from negative pi halves to pi halves, okay? And since pi is about 3.1, Bob, and divide that by 2, you're going to be close to 1.5, minus 1.5 to positive 1.5. Now, I may have that too big there, but we can live with it. Okay, where would we begin? Oh, and someone wanted to start at 0. What would 0 give us? Say again? You may have said it, I couldn't hear. Oh, the question was, when x is equal to 0, what's y? Now, if it's 0, very good. Okay, I've got 1 point. Give me another one. Let's say when x is equal to -1, what is your y? Negative pi halves. We got another winner. Okay, winner. Okay. And what happens when x equals 1? Positive pi halves. Okay, there's another one. Now, it's not a straight line, I'll tell you that. Okay? However, real close to the origin, it does act like a straight line. Very close to it. But here, you see that's gunning up too far, so this has the curve up, and this one has the curve down. And sure enough, as I said before, because when you do the sine function, you have horizontal tangent at minus pi halves, and another one here, you have vertical tangents here. So that's basically what it looks like. I don't mess around with the other points. You can if you want to, perfectly fine, but get the inputs, the intercept, and sort of get the values close. That's what it looks like. That's my rendition. You want to see how they do it? Say again? Sure you do. So next slide anyway. By definition, the equation y is equal to inverse or arc sine of x and sine y is equal to x. Those are equivalent equations. That's where I started before. I'm starting to do it this time too. Okay? And that's equivalent for any values for your y going from minus y halves to pi halves, any value x from plus or minus 1. So, but you see this one, plus or minus 1 on your horizontal axis, and the minus pi halves to pi halves on the vertical axis. So, you set up those points. They do this little table. If that's helpful to you to pick out points in between, go for it. Now, here's a little hint from me. I wouldn't use minus pi fourths and pi fourths because I don't know where square root 2 over 2 is. I sort of do. It's 0.707. Okay? But it's easier to me to use minus pi thirds and positive pi thirds because that would be, no, that's not easier either, is it? So, no mind. That one's as good as the other one. Okay? Actually, if you just use these two and those two and that one, that's going to give you 5 points. And that would be good enough, I think. But anyway, you can use any values you want to. You got calculators, you can plug them in. Okay? So to plot those points, plotting this one, and that one. And if you want to do the 1/2 pi 6 and minus 1/2 pi negative pi 6, you can put those in. You see, this is almost a straight line here. But then it goes up to here, goes down to here. Okay.
That's why you do more of the points in the C.
What's that?
That's why you do.
Yeah, they do a few more points just to get you going in the right direction. What I did, I said, you know this is almost a straight line. So I do those in without those 2 points and then curved up and curved down. Make sense? All right. Note, it is a reflection across the line y is equal to x of this portion here. So what I'm going to do is go back here because I have a little more room to work. And if you had plotted a few more points here, done this as approximately pi halves here, and this is approximately negative pi halves here. But then, now, do you want this in dark blue, or would you rather have something that contrasts a little better? Huh? Dark blue's okay? Okay, if you plotted on the same graph, y is equal to sine x, okay, you know, and if that's pi halves, this will be 1, and this would be minus 1. Okay, if you plotted it here, it would be 0 here, I'm sorry, minus 1 here, 0 here, plus 1 here. Okay, I put that in the wrong place, sorry. Here. Okay. Oh, goodness gracious, get back. Okay. Yeah. This would be down here. Okay. If you plotted this, okay, and then did your line y is equal to x, oh, goodness, it didn't take. No, wrong. There we go. Red. Okay. Sure enough, they do reflect across that axis. They're awfully close to the same thing here, but they deviate here, deviate there. So yeah, that's what, when you plot them both on the same axis, you get that. There should be just a little separation here, but not very much. Okay? All right. Be sure you see that figure 4.52, which is that? Yeah. That was the previous one. Shows the entire graph of the inverse sine function. Make sure you go from minus 1 to 1, from minus pi halves to pi halves vertically. Okay. All right. Remember that the domain of y is equal to arc sine x is the closed interval minus 1 to 1. The range is the closed interval minus pi halves to pi halves. Yeah, we did that right at the beginning. Okay. There's a checkpoint there. I would definitely do the checkpoint as well. What's that? 1 more minute. So I think next time we'll start with other inverse trigonometric functions. But we did get enough covered that you can do a few homework exercises. You can do number 5. You can do number 17. I think you can do, well, maybe not. We didn't do calculators, so we'll come back and do that. So 5 and 17, I know you can do. We will see you on Thursday.